Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to follow along on our previous video about calculating bearing resistances in timber. And in the previous video, we talked about, in the Canadian Standard 086, how we go about calculating perpendicular to grain resistance, which is the bearing resistance. That is bearing for a piece of wood sitting on something else on the side grain, not on the end grain, but on this side or on this side. We looked at how it looks like a crunching bundle of straws, and we talked about the two different cases that we have for this kind of design. One where we just have a localized compression perpendicular strain, like shown up here, where it's not the full depth of the member that gets compressed, but the compression strains branch out into shear before they get to the bearing supports at either end. And the second case, which is compression perpendicular through the full depth of the member, where the entire depth of that member is experiencing that compression stress. And in that case, we have a very long L, which means that we're going to get more deflection for the same amount of strain. And now what I'd like to do is look at some application examples, just not in terms of numbers, but just in terms of qualitatively. If I have different situations on a piece of wood for bearing, which equation do I use in order to calculate the bearing resistance, and what factored load am I going to compare that resistance against? Because it depends on which kind of resistance I am calculating. So I'm going to start by drawing out an example. Okay, so here we have a big wood beam. It has some joists on top. It also seems to be sitting on a bit of an undersized joist on the right. Let's make it a little bit bigger, just for the purposes of looking reasonable. Let's say this is sitting on a bigger beam here. Oops. Okay, so this big beam is sitting on a beam at the right and basically a steel column at the left, and it has two joists on top. And I want to calculate, I want to find out all of the different bearing checks that I would have to do for this assembly. So there is bearing of the joists on the beam. Then conversely, there's bearing of the beam on the joist. So the joist applies a load to the beam, and the beam conversely applies a load to the joist. So there's bearing checks for both directions there. And in addition to that, we have our regular kind of bearing check due to the localized compression perpendicular right below the member. But we also, in this case, have a through member squeezing bearing check for the joist on the left. And why do we know we have to calculate that one for the joist on the left? Because that joist is located within D, that is the depth of the member, from the support on the bottom. So if I have two loads, one on either side, and if one is close enough to the other that the perpendicular distance between them is less than D, as I've shown here in green, then we need to check the basically effect. It's called effective loads applied near the support, or what I like to call the squeezing load. Okay, oops. Okay, so what checks do we need to do? So what checks do we have to do for compression perpendicular strength in this example? And we have 4 different timber elements, and I've numbered them 1, 2, 3, and 4. And so what I'm going to do is I'm just going to list for each timber element, what checks do we have to do? Okay, so for 1, which is the beam. This is the big beam that goes horizontally across all. Okay, the first one is I need to check the resistance of the beam sitting on top of the steel column. That's in this location right here. So at that steel column, I have to check the direct resistance. This is just the first check I'm doing, okay, which is just the direct local resistance of the steel column pushing on the beam. And with what load? With the full load of the steel column. So the steel column is applying a load of 15 kilonewtons to the bottom of the beam. So the QF that I'm checking at here for my QR is 15 kilonewtons. And this QR is the all applied loads QR. All applied loads QR. Okay, so this is just the local one. Now, why haven't I checked the squeezing yet? I'm going to, but I'm going to do it separately. So first I'm going to check local bearing, so that's effective all applied loads. And then after that, I'm going to check the squeezing, which is like a separate additional check on top of that. So the second one would be just the same thing as the steel, but at the joist. Number 2. Okay, so the joist that's sitting on top, that's this one right here. I'm going to check what is the bearing resistance of the beam itself underneath that joint. Okay, so that's going to be QR. I'm putting a little 1 here just to indicate that it's the resistance of beam 1, beam number 1. So it's the strength of beam number 1 that's going to come into play in this QR. And for this one, the QF is the load of the joist onto the beam, which is pretty straightforward. So the beam is applying 5 kilonewtons. Joist number 2 is applying 5 kilonewtons to the beam. So the beam must have a resistance of at least 5 kilonewtons to that load. Then the third, and this is the tricky bit now, is near the support between the column and the joist. And joist 2. So this is the squeezing check. Okay, so this one is going to be QR1. It's still 1, but this is prime. So that's because this is a 2/3. It's the one with the 2/3. And this one has to be greater than or equal to what? Well, what I have to do here is I have to look at what is the load that's going through the beam from top to bottom, okay? So here there's 2 different sources of load that go to the support 15 kilonewtons. One is coming across, that's not a very good color. One is coming across from the 20, right? 10 goes one way, 10 goes the other way. And then 5 is coming through here, right? So this is 5, this is 10, right? And that makes up 15, but what is the portion of that load that's actually just the portion that's doing the squeezing all the way through? It's only the 5. So that means here I'm going to only check this against QF equals 5 kilonewtons. Now certainly you might say here, well, you know, why do I bother doing number 2? Because this one's going to govern, because the QF is the same, and the QR is going to certainly be smaller for number 3 than it is for number 2. Well, that is probably the case, but don't forget that for number 3, I use an average area between the area at the top and the area at the bottom. So we might not necessarily get a smaller resistance in 3 than we do for 2, because the area might be bigger. So I suggest you check both. Okay, then number 4 and 5 are a bit easy because I just basically have, for the beam, I have to check the bearing of number 3 on the beam here, and number 4 pressing on the beam. So I'm just going to check those 2 for local. No squeezing effects at either of those ones because none of the supports are not within D of each other. And when I do those, I check them against, obviously, the loads that are being applied at joist 3, which is 20, and at joist 4, which is 10. Okay, so now I've checked all of the loads coming on the beam, right? So I've checked the beam strength. Now I have to conversely check the strength of the joists because the beam is bearing up on the joists. Just as the joists are bearing on the beam is providing a force to the joist in the opposite direction. So I'm going to check those ones. These ones are going to have different resistances potentially because the joists might be made of different material than the beam. I mean, the joists could be timber, they could be lumber, and the beam could be glulam, for example. So for each joist, I have the one check, QR for joist 2, greater than or equal to 5 kilonewtons, which is the load that joist 2 applies to the beam, and conversely, that's the same load that the beam applies to the joist. And same for joists 3 and 4. Okay, in practice, if these are joists, I mean, the one on the right, number 4, is obviously going to be a bit bigger, but for example, if 2 and 3 are the same size joist, then their resistances would presumably be the same, so that'll save you a bit of work. But, you know, overall, you can see that all these bearing checks need to be performed in order to prove that the bearing works, and that could be quite a bit of work. So just be comprehensive with doing all the checks and pay particular attention to the fact that I might have the squeezing check at times when I have loads on either side of the member that are within D of each other, where D is the depth of the beam. Next, we're going to look at the calculation of the different parameters that are used in the bearing resistance equations.